In this video, I'm going to be taking a look at 3 different types of acid-base questions that you need to know before you write your exam. The first type of reaction is a neutralization or titration type of reaction. Now these reactions will reach equivalence point or endpoint, which we know is where there is a color change. Now the equation that we use to solve these types of reactions is going to be CaVa divided by CbVb equals Na over Nb. It's also important for us to know our reactions. For example, a strong acid plus a strong base will give me a neutral salt and water. The second one is a strong acid plus a weak base will give me an acidic salt plus water. And the third type is a weak acid plus a strong base will give me a basic salt plus water. And now it's also important for us to know for each type why the salt is either neutral, acidic or basic, and that we need to show using hydrolysis.
It is found that 40 milliliters of a 0.5 mole per dm cubed sodium hydroxide solution is needed to neutralize 20 milliliters of vinegar. 7.5.1 says calculate the pH of the sodium hydroxide solution. Now sodium hydroxide is a strong base, and so when it breaks, it's going to form Na plus and OH minus. The ratio of NaOH to OH minus is 1 to 1. Now in order to calculate the pH plus POH is going to equal 14. That means pH is going to equal 14 minus, and POH is minus log the concentration of OH minus, which we know is going to be the concentration of the NaOH. So pH is going to equal 14 minus log of 0,5, and that's going to give us an answer of 13,70. Now taking a look at 7.5.2, calculate the percentage of ethanoic acid by mass present in the vinegar. Assume that 1 milliliter of vinegar has a mass of 1 gram. So if we have 20 milliliters of vinegar, that's going to be 20 grams of vinegar. So what we need to do is figure out how many grams of ethanoic acid is in the 20 grams of vinegar, and then we can calculate the percentage. So we'll start with the formula CaVa divided by CbVb is equal to Na over Nb. Now from the reaction, which I haven't put here, the reaction is a 1-to-1 ratio, so 1 over 1. The concentration of the acid is what we don't know. The volume of the acid is 20 divided by the concentration of the base is 0,5, and the volume of the base is 40. Now when you solve for Ca, you get 1 mole per dm cubed. Now from here we can calculate the mass that's in the 20. We can use the formula C is equal to M over capital M times V. The concentration of the acid is 1. The mass of the ethanoic acid, which is what we want, the molar mass of ethanoic acid is 60, and the volume of the acid was 20 over 1,000. In this formula, we do need to convert it to dm cubed. So when we solve for mass, we get mass equals 1,2 grams. So this is 1,2 grams of ethanoic acid in 20 grams of vinegar. So that means the percentage is simply going to be 1,2 divided by 20 multiplied by 100, and that's equal to 6%. Now taking a look at question 7.6, the sodium ethanoate CH3COONa formed during the above neutralization reaction undergoes hydrolysis to form an alkaline solution, so basic. Write down an equation for this hydrolysis reaction. And so what we need to do is we need to analyze the salt CH3COONa. That's going to have 2 ions. One is going to be the CH3COO minus, and the other is going to be the Na plus. Now this came from a weak acid, which means it is a strong conjugate base. This is going to undergo hydrolysis. So the CH3COO minus plus water is going to give me, so if this is going to act as a base. That means this is going to act as an acid. This is going to donate a hydrogen there. So we're going to get CH3COOH forming, plus if I remove one hydrogen from water, I'm simply left with OH minus. The formation of OH minus makes the salt and the solution basic.
The second type of acid-base reaction that we could get is called a partial neutralization. Now in partial neutralization, there's no endpoint or equivalent point that is being reached. There's always going to be something that's in excess. If there is an acid in excess, then the pH of that solution will be less than 7. If there is a base in excess, then the pH will be more than 7. So the steps that we generally will follow is first to try and calculate the number of moles of either acid or base that's in excess. Then we need to convert this to concentration, but keeping in mind something called additive volume. And then the last step is to calculate the pH. During a titration of 25 cm cubed of 0.1 moles per dm cubed, sulfuric acid is added to an Erlenmeyer flask and titrated with a 0.1 mole per dm cubed sodium hydroxide solution. Question 7.3.3, why is bromothymol blue used as an indicator? It's so that we can figure out or determine the end point of the neutralization. Question 7.3.4, calculate the pH of the solution in the flask after the addition of 30 centimeter cubed of sodium hydroxide. The end point has not been reached as yet. So let's start off by writing a reaction. So the reaction between sulfuric acid, H2SO4, and sodium hydroxide is going to be H2SO4 plus 2NaOH is going to give us Na2SO4 plus 2H2O. Now for the H2SO4, we know the concentration and we know the volume. We can calculate the number of moles. So number of moles of acid is going to equal C times V. The concentration being 0.1, the volume 25 over 1,000. That's going to give us 2.5 times 10 to the minus 3 moles of H2SO4 at the beginning. We can also calculate the number of moles of base. So the number of moles of the base is going to equal C times V. The concentration also 0.1, but the volume is 30 over 1,000. And that's equal to 3 times 10 to the minus 3 moles. And this is of NaOH. Now, from here, we can calculate how much of base we actually needed to neutralize the acid. So we can use a mole ratio here. So number of moles of base needed to neutralize acid. So the ratio here is a 1 to 2 ratio. That means we're going to need number of moles of base is going to equal 2 times 2.5 times 10 to the minus 3, which is equal to 5 times 10 to the minus 3 moles of base. Now bear in mind, we only have 3 times 10 to the minus 3. We have less base than we actually need. So that means the acid is in excess. Now we can calculate how much acid is going to be left. So next point here is going to be how much acid was neutralized. So we're going to use the base here, since the base is the limiting reagent. We're going to say that the number of moles of acid is going to equal half the number of moles of the base, because it's a 2 to 1 ratio. So half of 3 times 10 to the minus 3, which is equal to 1.5 times 10 to the minus 3 moles of acid that was neutralized. Now from here we can calculate how much moles or how many moles of acid is left over. So we can then say moles of acid left over. So that's going to be how much we started with. So 2.5 times 10 to the minus 3 minus how much was neutralized. So 1.5 times 10 to the minus 3. And that's equal to 1 times 10 to the minus 3 moles of acid that's left. Now, because remember the acid is in excess, we expect a pH that's going to be less than 7. So
Once we have the moles of acid left over, we can calculate the concentration. So the concentration of the acid, that's going to be concentration is equal to number of moles divided by volume. So the number of moles here, 1 times 10 to the minus 3 divided by, now the volume, as I said before, we need to keep in mind additive volume, because this number of moles is now sitting in a larger volume. It's sitting in a volume of 25 plus 30, which is 55. So 55 cm cubed divided by 1000 to get dm cubed, and that's going to give us a concentration of 0,018 moles per dm cubed of H2SO4. Now we're nearly at the end. We can calculate the pH. So the pH is going to equal minus log of the concentration of H3O plus. So that's going to be minus log of the concentration. Now remember, H2SO4 is a strong acid and it is diprotic, meaning that one molecule of H2SO4 is going to produce, 1 mole is going to produce 2 moles of H3O plus. So it's going to be 2 times 0,018, and that's going to give us an answer here of 1,44. Question 7.2 says a certain fertilizer consists of 92% ammonium chloride. A sample of mass X grams of this fertilizer dissolved in 100 centimeters cubed of 0.1 mole per dm cubed sodium hydroxide solution. The NaOH is in excess, the reaction is given. 7.2.1, calculate the number of moles of sodium hydroxide in which the sample is dissolved. So this is simple. We're simply going to say number of moles is equal to CV, concentration 0,1, the multiplied by the volume, 100 divided by 1000, and that's going to equal 0,01 moles of NaOH. They then tell us during a titration, 25 cm cubed of the excess sodium hydroxide solution is titrated with a 0,11 mole per dm cubed HCl solution. They tell us that they used 14.55 cm cubed of the HCl and the endpoint was reached. They give us the reaction and they ask us to calculate the mass in grams of the fertilizer used at the beginning. So because we know the volume of the acid and we know its concentration, we can calculate the number of moles of the acid that was used. So 7.2.2, the number of moles of the acid is going to equal concentration times volume. Concentration 0,11, volume 14,55 divided by 1000, and that's equal to 1,6 times 10 to the minus 3 moles of acid that was used. Now from here we can do a mole ratio to figure out the number of moles of base that was used. So the number of moles of base, because it is a 1-to-1 ratio, is also going to equal 1,6 times 10 to the minus 3 moles of the base. Now bear in mind, this is in 25 cm cubed, and this is the excess base. Now to draw us a picture, we had some excess base in 100 cm cubed. They took out 25 of it, so we have 25 here. And we know that in here there is 1,6 times 10 to the minus 3 moles that's in excess. Now what we want to do is figure out how much was in excess in the 100 cm cubed. So we don't know this. So we can do a simple ratio. We can say that 1,6 times 10 to the minus 3 is 25 cm cubed. That means 100 is going to be x. Now we can cross multiply, and x is going to equal 6,402 times 10 to the minus 3 moles of NaOH that was in excess in the 100 cm cubed. Now from here we can calculate the number of moles of NaOH that was actually used in the first reaction. So we know at the beginning we had 0,01 moles of NaOH. We then know that after reaction 1 we had 6,402 times 10 to the minus 3, that's in excess. So we can, if we subtract these two, we can get how much was used in reaction 1. So if I subtract it, I'm going to get 3,598 times 10 to the minus 3 moles of NaOH that was used in reaction 1. Now from here, I can then do a mole ratio. The mole ratio for NaOH to NH4Cl is 1 to 1. That means 3,598 times 10 to the minus 3 moles of NH4Cl was neutralized or reacted in reaction 1. Now from here we can calculate the mass. So the mass here is going to equal number of moles times molar mass. Number of moles is 3,598 times 10 to the minus 3. The molar mass of NH4Cl is 53,5, and that tells us that we have 0,192 grams of NH4Cl. Now, we're not done yet because they tell us that this is 92% of the fertilizer. So this is 92% of the fertilizer. We want to know how much is 100%. So 100% of the fertilizer will be X. We can then cross multiply again. That means X is going to equal 0,209 grams.